So this is a kind of an open discussion to discuss a bunch of the issues, the ethical, philosophical, and scientific issues. You've got a panel of 4 crack local experts from NYU. Top-notch experts. We have 2 philosophers, 2 scientists. Matthew Yao will talk to some of the ethical issues. Ned Block will talk to some of the philosophical issues. And David Purple and Marissa Carrasco will talk to some of the fundamental scientific issues. The way it'll work is they'll each give presentations for about 5 minutes, starting with Matthew. The thought is after each presentation, we'll open up for a few minutes, maybe 10 minutes or so of discussion of the issues just raised. And then maybe after an hour or so, we'll open it up for a general discussion where people can raise issues they think need airing, and for discussion both by people on the panel, speakers, and anyone who's around. Okay, but now we'll turn things over then to Matthew for an initial presentation.
Great, thanks. Thanks, Dave. We just had a whole session on ethics, and as Nita has said, many of the ethical issues are not going to be in sort of the new brain mapping technologies. They're not going to be very new. Initially there's going to be standard issues about human subject research. When you start experimenting, using these technologies in humans, there's going to be issues about risk, informed consent, safety, etc., etc. And those are important issues that basically pertains to all new technologies. So I'm not going to say very much about that, but if you want to raise it, happy to discuss it. So to ground the discussion, what I'm going to try to do is DARPA, about 3 weeks ago, so DARPA is the Defense Advanced Research Projects Agencies, the government's defense agency, just released a grant call about 3 weeks ago. And there were 2 grants. One is called the SubNets, and that's the Systems-Based Neurotechnology for Emergent Therapies. And it asked researchers to develop novel wireless devices such as deep brain stimulators that can address neurological disorders such as post-traumatic stress disorder, major depression, and chronic pain. The second one is about it's called RAM, Restoring Active Memory. It calls for wireless devices that repairs the brain damage and restores memory loss. I'm going to focus just on the first one, just to sort of ground the discussion. So many war veterans are coming back with PTSD, post-traumatic stress disorder. Many they have nightmares, flashbacks, some are suicidal, some have, and many can't live normal lives. And for some of them, the medications are just not helping. I mean, there are drugs like propranolol that they're taking to try to dampen these sort of emotional memories, but they're sort of not as effective as they could be. And then deep brain stimulation is this technology that involves implanting a medical device that sends electrical impulses to specific parts of the brain. And this has already been used. It has already been shown to have therapeutic benefits for Parkinson's disease, epilepsy, and major depression. And there's some evidence that DBS, deep brain stimulation, can also ameliorate the effects of PTSD. Functional neuroimaging studies have suggested that amygdala hyperactivity is responsible for the symptoms of PTSD. And there's some evidence that you can actually use DBS to reduce the activity of the amygdala to reduce the symptoms of PTSD. So what DARPA wants to do is DARPA wants a closed-loop device, and we can call that DBS Plus. Okay, that can monitor the brain's activities in a very general way. So they don't want it just to be targeting PTSD, but they also want it to monitor depression and all sorts of different brain injuries and diseases. And then the closed-loop device will sort of intervene in the brain when necessary. Okay? Okay? So for example, if the device detects a strong fearful response in the amygdala, then the device would send an electrical signal to slow or shut down the amygdala. And they want this sort of in 5 years, something with clinical application in 5 years' time. Whether they can do this or not, who knows? So what are some of the potential ethical issues of this DBS Plus? So DBS Plus is likely to share very similar issues as DBS. So what are some of those issues? So right now, people are already using DBS, and there are issues like authenticity and alienation. So some patients given DBS have said things like, I don't recognize myself anymore. So what happens is DBS can take away the tremor, but sometimes they also take away their urge to do things, their sort of their motivation to participate in life. So that's sort of one side effect of DBS. It's a known side effect. Another, DBS has also been known to provide unintended enhancements. So there are cases of patients who they get DBS, it doesn't stop the tremor, but they're actually feeling really happy. And so they don't want to get off DBS. And well, there's an ethical issue about whether you should take them off DBS because it's not doing what, it's not helping them with their epilepsy, but it's making them really happy, right? So there are sort of enhancement issues. And so I actually want to talk about the enhancement issues, specifically in the military, because that's what DARPA initially wants to do. And I think there's some really interesting issues here. They may not be new, but they're sort of interesting to draw out. So one thing that DBS, so this DBS Plus could use, for example, to preempt. So initially, it's going to try to treat PTSD, people who already have PTSD. But later on, you can imagine this sort of being used. So this, just one step away, hopefully it's not too science fiction-y, it can start to use to preempt PTSD. So suppose a potentially traumatic event has just taken place. You can imagine DBS Plus could be used to detect and categorize the emotional reaction, right? So you can, like tsunami warnings, you can have different categories, right? So if it's category 1, then it does nothing. But if it's category 4, it starts to slow down the amygdala. If it's category 5, it's really, really slows down the amygdala. And when the emotional response to a traumatic event is reduced, the memory of the traumatic event doesn't get consolidated as strongly into the long-term memory. So that's sort of roughly the idea. More generally, DBS could be used to modulate other emotions. So remember, DARPA was this sort of general device, right? It's not just for PTSD, but also for depression. So, and for military purposes, what could they use this for? Well, imagine that you have soldiers who go into battle who are, scared of being, they have fearful responses, they're afraid to go into battle, they're afraid to shoot somebody when they should be, pulling the trigger. So you can imagine that soldiers implanted with this device, DBS Plus can help reduce or even remove the fear. And it can also increase. So one way, you can sort of stimulate other systems, increasing sort of courage by sort of stimulating the adrenal, like increasing adrenaline. And these applications, they don't seem too far-fetched. I mean, once you have the implant, it seems like you can do and you don't even have to know that much about sort of the underlying, ideally they want to know more about what's happening, but it seems like right now we don't know very much about DBS, and we're already using it for clinical applications. So what are some of the issues here? Well, it might be thought that as long as there's informed consent from soldiers, then there are no ethical issues. And I think this would be too quick. Even if there were informed consent, there could be subtle forms of coercion at work, especially in the military, which should be taken into account. So for example, the military command structure is hierarchical. And so this could make consent less than fully voluntary. And there may be subtle forms of peer pressure. You might not want to let your fellow soldiers down. And those are subtle pressures that we should take into account. There are sort of, in bioethics, there are a lot of discussions about coercion and exploitation. My colleague, Colin O'Neill, works on this topic. And moreover, even if one did not agree to a brain implant, you may be at a competitive disadvantage. So imagine that someone's the commander and they have to decide who to pick to go into battle, right? And soldiers with brain implants might be more reliable under pressure than soldiers without brain implants. And so those raise certain very interesting issues. So here you might think, well, just as we ban doping in sports, maybe to avoid these ethical issues, what we should do is try to ban, have some sort of rule, some sort of policy and ban enhancements in soldiers, right? But it's not clear that this is going to work because, well, first of all, soldiers are already enhanced in so many other ways. They have night vision goggles, they're already taking psychopharmaceuticals like modafinil and propranolol. Guns, are a form of enhancement, overusing hands in combat, right? Second, in sports, fairness may be important, but as the saying goes, all is fair in love and war. So would any U.S. soldier want to voluntarily give up sort of advanced military weaponry just to level the playing field? But the biggest concern of DBS Plus that, when I talk to people about this topic is that people worry that this would lead to soldiers without conscience, who would kill indiscriminately in ways that are out of proportion to the good. And I think this is a very serious concern. But what I want to say here, and this is the point that I want to make, is that this actually may be a technical problem. So brain implants that shut down our sense of morality you might think they're morally indesirable. I mean, if you're fighting along someone who's sort of conscienceless, they might turn around and shoot you as well, right? So they're not really enhancements. So it seems like efforts should be made to make sure that we don't have, brain implants that we develop don't have these side effects. And so what this means for practical policy is that in the short term, we should be making sure that it's very likely that the DBS Plus that we develop in the short term are going to be imperfect in just this way, right? They're going to not modulate the emotions very well. So maybe in the short term, we should have some sort of ban on these type of devices. The interesting theoretical question I have is, well, what happens when we perfected this technology and have brain implants that would enable a soldier to kill at the right time, for the right reason, and in proportion to the good? Will we still have ethical problems using such technology? Thanks.
Questions or reactions?
I have one small comment, sort of from the side, which is, I suppose that what will really drive things in the military application in particular is legal responsibility, what the military thinks it can get away with without being sued by the families of the soldiers.
Yeah, that sounds very, very likely. Yeah. Do you think that's right? I mean, just sort of, this is a panel discussion. The legal constraint. Right, good, yeah.
Haven't we really achieved the same thing with hypermasculinization? In other words, like gang rape or, but the idea of testosterone or anything like that, achieving it with no implantation whatsoever. And so we don't need fancy technology to achieve that kind of thing. We just need, again, regulation of hormones or something like that, because we have evidence in all kinds of situations of hypermasculine behavior, whether it be at a fraternity setting or at a gang raping in India or wherever, that this is kind of acceptable, and we haven't had any moral constraints in these hypermasculine societies.
Right, right.
And that's no technology unless we do something to regulate those hormones.
Right, so, but I guess, so the question that I'm interested in is sort of what happens if you can perfect. So that testosterone, if you have that, sometimes it leads you to sort of immoral behavior, and so, but imagine sort of you get the right level for soldiers or something like that.
Right. So it would be a similar type of regulating system that you would need in those situations.
Right.
Yeah. Hi, Matthew. I was curious about another aspect of this, and that's that I can imagine there being a lot of resistance from the sort of soldiers' ethos to using fear-reducing or, fortitude enhancing deep brain stimulation. I mean, the idea would be that somehow, you want your courage to be natural, to be somehow summoned from the, by will. I mean, whether that makes sense or not, that's certainly an idea. And I mean, I can imagine the question of whether a Congressional Medal of Honor ought to be awarded to someone who had fear-reducing DBS plus and performed the sort of heroics that now, win the Congressional Medal of Honor, whether there'd be a little asterisk in the record books. I mean, so that I'm just curious, if I mean, that's a kind of pushback you weren't talking about.
That's right. Yeah. So I wish, is Pat still here? Because Pat sits on the committee she's just been nominated to be sort of on she's one of the ethics members for DARPA. And I'd be interested to know whether soldiers now dope, like the SEAL team that went into, to get, Bin Laden. Does it make a difference whether they took steroids or they took modafinil so they can sort of, I think they do, right? Like there's evidence that they already take modafinil. They already use psychopharmaceutical things. So there's no blemish. We don't say, oh no, they put a little star by these SEALs because they didn't really do it. Yeah.
Those are attention enhancers, they're not courage enhancers. It's not seen that way.
Right.
And I think it's something that is seen as reflecting on the quality of courage or fortitude in their acts would be resisted in a way that memory and attention enhancements weren't.
Yeah. That's good.
Okay, we'll take one more.
Yeah.
So clearly and indiscriminately killing soldier as a result of DBS plus is a problem, and I'm just slightly more concerned about what I'm concerned with that result, but I'm less concerned with that as with how they might get there. And I think it might be important to separate out a traumatic event that was a consequence of action that the soldier directly participated in with a traumatic event that the soldier may have witnessed as a part of the war, and it's difficult to determine levels of involvement, but I think for the purposes of argument, it's safe to say that that the trauma of an event that was directly participated by that particular soldier's actions may affect the soldier differently. So I'm running on, but if the consequences of that behavior are what drives future behavior, and your intent is to modify the experience of that consequence, then how, as you said, that effect is really a side effect and a technical problem. So how is that possible? If you're modifying the consequence, that has consequences. So how is it really a side effect and not just another side of the main effect?
So I guess we want to distinguish between cases where, say you want to commit a crime, but you're scared of doing it, and the DBS enables you to sort of commit that crime because now you're less scared, right? You're sort of, from cases where you're trying to do the right thing, but you're sort of scared. So were you talking about, and so you can imagine both cases, in either case, it could give you sort of, you could get trauma from what you're doing, right? Say killing somebody, right? And so the DBS would operate in the same way, I guess, so I take it your point is that if they were to operate in the same way, then that could be problematic, and that seems right.
More for PTSD
Yeah.
than for fear.
Pardon me?
More for the PTSD applications than for the preventing fear. So
Yeah.
It would lessen the trauma of whatever that soldier had just experienced.
But the trauma could be the trauma could be something that, it could be the result of an action that you perpetrated, right? It doesn't have to be something that you witnessed, right?
Exactly.
Yeah. Yeah.
Okay, we'll have a chance to come back to these issues more in the general discussion, but now I'll hand it over to Ned.
So I'm going to talk about something completely different, topic that's come up quite a few times. But so let me start with the bottom line, which is I have not seen in the course of these 2 days I have not seen very much of a rationale for any of these bottom-up approaches, whether it be the connectome, the activity map. The problem with those approaches, as many people have mentioned, is they threaten to drown us in a sea of useless data. So the reason why I think this data might just be totally useless is that nature has joints at many different levels. And we can theorize at many different levels. And the upper levels do not just emerge from data about the lower levels. Now, Tony mentioned the MAR hierarchy of computation at the top, algorithm, implementation. I think that thinking of things that way seriously underestimates the problem. The problem is there are different idealizations at different levels. I think a good example for thinking about this is the digital computer, where at the level of, we have a level of ones and zeros, which is quite useful for thinking about the computer. At a lower level, we have on-off devices that have intermediate states. It could be 4 volts, 7 volts, and then when we look at closely, we see some voltages in between. Maybe at a still lower level, it's quantized again. At a higher level, it's programming languages. So if you think about nature in terms of idealizations at different levels, you realize that there's just no substitute for having ideas about levels of nature, making proposals, testing those ideas, and the right way to do that is the way we do science now, which is to have people who have research projects, who have ideas, they apply for grants, a panel of peers decides whether those ideas are any good, and some people get some money and some people don't, and that's worked pretty well. The danger to me of this massive bottom-up approach, well, the possible benefit is it might bring more money to the sciences of the mind. That would be great. But the danger is that money will be siphoned off from good projects where people have ideas and have theories to test, and that money will go into this mindless stuff. So I think one way to see the problem is to notice that the areas where we understand, at least in my view, where neuroscience has done its best is in areas where we already understand things pretty well at a psychological level. At least we have an overall theory, and we can look for the realizations of those theories in the neuroscience, and maybe learn that the original theories were not quite adequate. And the area of the sciences of the mind where this is the most obviously true is in perception, where we have very good theories based on psychological data that we can then investigate the neural underpinning, where we can then investigate the neural underpinnings. If you look at any issue about the mind at the level of psychology, you see a lot of different ideas about the systems that can be investigated. So, for example, if you're interested in how people think about cognition involving number, there are 4 different number systems, and there's an analog magnitude system that we share with many animals that underlies the famous number line. There's a small number system. There's a language-based system that underlies the endings on quantified endings. And of course, there's the explicit numerical system involving the digits. I just don't see how this kind of these concepts would arise from a bottom-up approach. So, at least from what I've seen so far, I'm against the bottom-up approach.
Who knew Rafael?
So I have two comments. One is that I think you seriously underestimate the importance of methods in science, and particularly in biology. You have to realize that biology is still in early stages of discovery. It's a science which is not as mature as physics or chemistry or mathematics, where you can actually make numerical predictions about the systems. But we're still in the discovery phase, where we're still getting to know what we're dealing with, what is our phenomenology. And if you look back at all the revolutions in biology, and particular neuroscience, it's all a game of new methods. Whenever a new method has been introduced, this is when neuroscience has advanced forward in leaps. And that also leads me to the second comment I wanted to say, is that neuroscience has advanced tremendously, but it's getting to the point where I think it's fair to say that it's ready to grow into a big science model. And physics has particle accelerators, chemistry uses also particle accelerators, astronomers have these big microscopes. Meanwhile, neuroscience, which is dealing with something as important as the human mind, is still operating on the ma and pa store model of little labs doing little experiments. And there are certain things which cannot be done because they simply cannot be done by individual labs. There's a matter, this is the game of size. No? You want to build a microscope where you need to design a new objective, well, guess what? A single lab cannot do that, particularly on research funding. This is the type of project that requires 50 people coming from different fields. So I would argue also that a conceptual jacket that we've inherited, I've said it today and I said it yesterday, is just too small. Neuroscience is ready to grow, it's ready to become a full-blown science like its sisters, and this is why we should endorse this initiative, particularly those that are going to build new methods so that we can actually discover the new phenomenologies and build the bridges for finally with all the psychological phenomena that you're describing, that for which we still need to have proper data.
So look, the analogy with the discovery of the Higgs boson goes completely to the disadvantage of this bottom-up approach about the mind. They had a very well-developed theory which they wanted to test, and they knew how to do it, and they went ahead and did it.
Yeah, but
but we don't have that. What we have, we just want, this proposal is a proposal to collect data for we know not what.
So this is a misunderstanding of at least the brain activity map. The way we proposed it was to develop the tools so that anyone in the world, any neuroscientist in the world, could go and collect whatever data they wanted. The Higgs boson is an example of a precise developed science making very particular predictions. So let me point out that these particle accelerators are not built to test one single prediction. If you go to the Berkeley, Berkeley labs, that accelerator at the same time is being used by 60 groups of people testing 60 different predictions. And half of the time they find things they were looking for. And this is how science advances, through the new methods. They have access to these new methods.
The way to develop new methods is for people to have ideas about new methods, to propose them in a grant application, and have other people judge whether they're good new methods. So the thing is, we don't even know, as a number of people have pointed out, exactly what we should be measuring. So I just don't see how, I think the idea sounds good at first. Okay, we have a repository of data. People who have ideas can test their ideas with that repository of data. But
I made the argument yesterday, which I would reiterate today, that any neural circuit is built out of hundreds of thousands of neurons. The methods that we have today only give us access to very few of these neurons. And this is just like trying to watch this TV by looking at a single pixel. I think it's obvious that we don't have the right methods to access the full picture. So, and I ended up with a quote from Sidney Brenner that, new methods, new discoveries, and new ideas are as probably important in that order. And I would state to that quote that if you go to neuroscience and the origin of the neural doctrine, how this is tied up to the Gaudian method, how the Hubel and Whistle method is tied out. Hubel was the same person. The person behind the Hubel and Whistle model is the same person that discovered the electrode. It's the same guy. The methods guy was the one behind So I think it's obvious in neuroscience that we need this new method to see the full picture, and then this method will generate the data, and hopefully with this new data, we finally someone will see what we're supposed to look for.
So let me ask you a question. Why don't you propose to map out the position and velocity of every elementary particle of the brain? Surely there is some level of detail which is too detailed.
Yes, I think the philosophers know about that. That's called the scale problem that was brought up today. And I completely believe that. I think there's an emergent properties game here, and that we can actually ignore or abstract a lot of these atomic level properties.
I'm broadly sympathetic to most of what you said, Ned, except maybe the part about the research funding model working, which seemed to be implicit, and I don't buy for a minute, but that's a story for another day. Here's a way in which I'm slightly less sympathetic. I think what we really want are bridging laws. We want to be able to bridge between different kinds of entities. And for me, the salient example is always between Mendel's factors and the structure of DNA. And to do that, you can't do that entirely top-down. So Mendel took it as far as you could top-down, but then you needed Watson and Crick and Avery and so forth to do some bottom-up stuff. I don't think we need to map out the whole brain, but I do think we need, I'll call it a cortical column. It might not actually be that unit, but we need some kind of unit like that in order to build the bridging laws. We're not even going to get from there to a parser. We're going to get from a bridging law to some intermediate state, and then we're going to be able to figure out the things that psychologists like me care about how we do parsing or how we do scene recognition, these sort of more complicated things. But I think we need some kinds of bridging regularities, and to do that we do need to understand something at roughly the level of a cortical column. So,
I agree with that.
well,
Yeah,
so that's a little bit.
I did not mean to suggest that there should be no study of, no neuroanatomy, and no.
Well, so then the question is where do we want to draw that
We need
line?
both bottom up and top down, but the idea of putting all our resources into a massive bottom up project seems to me to be.
I won't endorse that. But.
Okay, over here.
I think that something we need to remember is that, at least in the case of Sean's EU version of the brain mapping initiative, that there are people making theories. There's an entire department that's doing that at the same time. I mean, there was a large emphasis on top.
8% of their budget, and that includes ethics too. So it is large in absolute dollars, it's small in terms of proportion of their effort.
Yes, but there is some effort to do not parallel studies, but have like studies that run the entire gamut that sort of would appeal more to the traditional view of scientific discovery. And but there are also ways that bottom-up has worked in other fields like data searching engines like Google or Bing, where they have a bunch of results and web crawling information, and then they derive patterns and they make an algorithm that works. And in terms of Google, they're fine with just an algorithm because it works and it makes money for them. But it's not that hard to then look at the algorithm and the patterns that arrive from all the data and ask, why does it do that? What does that mean? And then ask questions about the algorithm and about its application. So,
Let 1,000 flowers bloom. But yeah, so I don't deny that it's good to try that kind of thing, but not so to the extent that it uses up so much in the way of resources.
Okay, let's now move on to David Purple.
I actually feel a lot like Ned, but I also have to run a lab, unlike Ned. So I'm going to take a slightly different approach to this because I do care about content. I said it's pretty interesting that the neuroscientists yesterday and today kept saying that this is about the mind. For instance, you said that 2 minutes ago. The most important thing is that neuroscience is about dealing with the human mind. And we didn't actually hear much about that. So I want to go down this path a little bit. So I actually am somewhat enthusiastic about all these big projects for reasons that might be a little weird. Namely, I think there are going to be lots of accidentally interesting findings in the development of technology. We're going to learn a lot of weird things. But there's a couple of things that for me are missing, and I want to articulate 2 things that are missing. One is so there's two problems, the ohm problem and the mapping problem. Let me tell you what those two problems are in my mind after listening to this. The ohm problem is, well, we now have heard about the genome, the proteome, the epigenome. Now we're talking about the connectome. Yesterday from Tony Zador, we heard about the projectome. And we have the brain activity map ohm. So that's very ohmic. But there is one, if this is about the mind, there's one absolutely crucial one missing, and that has not been discussed, namely the cognome, as the parts list of the human mind. And since we don't have visual aids, I brought my own visual aid along to make this more memorable for you. This is a cognome. This is the garden, Noam Chomsky garden gnome. You gotta love New York. You can get everything in New York. So Noam Chomsky, who's I think it's his birthday today or something like that. So Gary chose me. So the gnome. Noam invited us to think about, in the context of language, about the elementary parts list, right? About, in this case, about language, sort of the representations and computations about that. And so that formed the basis for the computational theory of mind. And so what I think, maybe we should take a little bit of this money. This is not going to go away, this initiative, and it probably shouldn't. So let's get some of the money for us. We want the Human Cognome Project as well. Okay, so because we need the parts list of the human mind. Now, why should you care, though? Why should the neuroscientists care? Other than, the neuroscientists should fund psychology. Why should you give me your money? You should give me your money because you have a real problem, namely the problem that Gary just raised and that came up, I think, in Tony's, it came up a lot today, this bridging problem, or the failure to actually articulate linking hypotheses at the right level of granularity to really form relationships between neuroscience and cognitive science. So the mapping problem is a serious one, because we want a map of the set of primitives that come from the cognitive sciences, from the Human Cognome Project. These are, let's say, at the level of computational analysis of something, and the set of primitives that we get from the brain initiative, the brain activity map, the Human Brain Project, and so on. So that's going to be a parts list of one type and a parts list of a different type. And the practical problem that we all face, including me, when I work on neuroscience issues, is, well, what are these linking hypotheses or these bridging hypotheses? What's the right level of analysis to formulate them to actually do hands-on research? And that has been missing completely. When Gary tried an idea out this morning, that's a hypothesis that one can test. But in general, if the big goal is to map to the human mind, which I think we would like, or behavior if you want, then you have to have these linking hypotheses. What would progress be like? What would it look like if we succeeded? We heard a few examples. Cori Bargmann mentioned that the work on C. elegans, that you can kind of see some projects that work. There's really elegant stuff on sound localization in the avian versus mammalian brain, where the circuit actually is like an explanation for the behavior. In general, what would be worth remembering, whether it's via MAR or philosophy or Wilfried Seller or something, is the notion of we are seeking explanatory adequacy, not descriptive adequacy. We want causal mechanisms that are an account of the basis of perception, cognition, language, or whatever it is. And we can't just punt on that. We can't just pretend that it's all correlations because we have a lot of interesting neuroscience and some good psychology. That's not good enough. If we're going to spend this much money, our yearning should be higher. It should be for real causal explanations. And so part of that, I think, should be that we have scientific psychology, not folk psychology, well developed, or the cognitive sciences, and that we have a Human Cognome Project to provide the linking hypothesis. And there we have great examples of very mature research in perception cognition, and actually we're going to hear such an example in a second. But so my pitch is the Human Cognome Project, or and further endorsement of the computational theory of mind, which is in part thanks to this guy.
This is, of course, exactly what I was endorsing in my own talk. There are two levels, though, at which you could do it, and I want to suggest why I think the one I proposed is the more feasible one. So the other level to do it would be at the level of the painting that Cori had of the Mardi Gras, where what you do is you catalog all the behaviors. I think if you had the word cognome, you could take it to mean let's categorize all the human behaviors. And I think that that's probably a lost cause. And I think the right level to do it is at these cognitive primitives that you can do the bridging for. And so I think defined that way, I think it's a great idea, and I hope people will join me.
So I actually am very sympathetic to what you said. In fact, I discussed this corresponding with Chomsky about this issue, and he sent me to your colleague Marantz, and we even looked at data together and talked about these things together. So I have nothing against what you propose of looking at linguistics in particular to give the primitives, the computational primitives that could be present in a cortical column. And then we could actually try to tie this up with the data coming from above. But without having the data coming from below, you're not going to be able to tie this to anything. So I'm very supportive of what you said. And in fact, our third goal in our brain activity map, as we proposed to the White House, was to have a significant amount of resources developed to the development of theories based on the data. And this is a little bit what we had in mind.
Yes, I'm a psychiatrist, and I've been sitting here the last couple of days, and I've been very excited by what I've been hearing. And though I guess I deal with the mind in almost every day in some form, and I guess I'm struck by what I see as a kind of reductionism. I always think of the mind as also including the social context, language, culture, and I'm not hearing that today. It's almost, I hear this research almost as if one wanted to study society, one would kind of focus on a single individual and somehow learn about institutions. It's on that level. It seems too narrow to focus on the biology and even the neuroscience. Neurocognition seems a little bit too reductionistic in many ways. So I wonder where the social aspects are in this. I think mind is social too. It's embedded in the way we think. So, any thoughts?
And that did come up in some of the talks, I think yesterday as well, that there's social neuroscience, but the problems there remain the same, right? You have to decompose, for instance, social interaction into a set of primitives that have the interaction such that they yield that social interaction, right? So whether it's for you as a physician, the patient, or anything. So social neuroscience isn't a different kind of problem, it's just the same kind of problem in a different domain. We still have to decompose stuff into the things that have traction in terms of the neurobiological vocabulary. I think it is a part of current research. I disagree that it wasn't part of this conference so much, but it's a very active area of neuroscience research. Whether it's any good,
the bottom-up approach doesn't seem to take social factors into account at all. It's divorced from context.
That seems independence, right? You can take, those seem slightly different kinds of questions, whether it's purely bottom-up or you're interested in social neuroscience or social psychology or clinical. You can try it both ways, but they don't seem to need to be necessarily related, as far as I can tell.
Great. So David, no one exceeds my enthusiasm for the cognome. I think it's a great idea. The problem I think that you face in the context of this sort of world of brain mapping projects and so on and so forth is that the behavior that people are increasingly seeking is the behavior of tractable organisms. And so, I would love to see the study of language come front and center in this, but it's actually going to be the study of decision making in rodents, or the study of behavioral tools for making decisions about organisms in whom the biology,
or sound localization is an example where
that's worked. But the question I have for you is, what's the best way to bridge the species gap as well as the behavior gap? So in addition to looking for behavior that you can link to brain function in humans, you also need to have some kind of connection between higher brain function cognition and the kind of brain function that you can measure reasonably in experimental animals. I wonder if you had any thoughts about how that would go, or how you would facilitate that.
I guess my own hunch about this is that many of the, so let's take let's take what I work on.
Speech language.
Let's take speech perception, for instance. Let's forget language. Speech perception, the set of subroutines that take squiggles in the ear and create abstract representations that make contact with mental stuff that's stored. There, some of the subroutines seem very likely to be generic computational things that are reused across species. So you can learn a lot from looking at whether it's in a macaque or whatever. So I think so this is, again, back to this decomposition and finding linking hypotheses. If we decompose it at the right level of granularity, my assumption is that some of the subparts, I don't know, what you mentioned this morning, divisive normalization, maybe that's the kind of operation that's actually recycled because it's a form, because it's a property of the circuit that's useful in a bunch of different things. So learning about speech perception will be informative for the human case, but also tell us about, let's say, macaque or whatever. So I think it's a question of the nature of the decomposition.
Yeah, so I just want to be clear. What I'm worried about is the difference between the parts list for human behavior and the parts list for rodent behavior.
It will be different, but there will be overlaps, right? And it's the overlaps that we can get some traction on with it. So we need to figure out which ones those are.
I was about to tell you about eating, hearing, and reproducing. So,
I think I'm not going to go in that direction, but those are certainly in the ballpark that we could try to get some.
No, I think I want to pick up a thread from that, from what you said, and actually from the point about psychiatry, just to say that I think there's tremendous hunger in the field for principles that you can apply across these levels. And I would say that an example of that has tremendous support is the reward prediction error hypothesis about the role of dopamine in the brain, right? So you have something that's important in human addiction. It serves to explain some of the roles of drugs of abuse. You have something that you can model in animals, and then you have something that really involves a theory that involves cells and molecules and synapses. And it's such a beautiful model that even in the cases where some of the data aren't really supporting it, when you look in the activity, it's very hard for people to give up. But I think it's an example of the sort of process that would be a cognitive process, at some level a really interesting process from a whole psychological perspective, and then would move all the way down to circuits, cells, and molecules. So I think that's a real goal.
Yeah, no, I'm very excited about that. But there's an example of a set of operations in the reward prediction error case that's actually is going to look very different depending on which part of psychology you look. Right. So, for instance, it's all over language processing these days. There are these predictive models of that. That's going to be a little bit different in its implementation than, say, the addiction case. So that becomes a MAR question. Is the reward prediction error type of computation or circuitry generic across every kind of problem, or does it matter what the input array is? That's a very promising one because it seems to be conserved across a lot
and
of
it becomes an
askable
question,
yes.
then, exactly the question you just asked.
Yes.
Okay, let's move on to Marissa Kraska.
Thanks. So I want to touch back on some of the topics that have been talked about, but I want to stress first the importance of behaviors, and without denying at all, of course, the importance of methods. I've been recently talking to a number of colleagues in different panels at NSF and at NIH in different workshops, and I have to say that the cognitive psychologists are very concerned because they feel that even though there's some lip service to behavior, when we talk about behavior, it's not involving the behavior that we feel that we can contribute to its understanding. That is, there's no importance on understanding how cognitive processes affect behavior, and there are some cases where we can actually bridge species gap that Tony was referring to. For example, we know a lot about in perception about the similarities of the macaque and the human, and furthermore, we know how some of the processes may be affected in the same way by some higher cognitive processes. So I'm completely with Gary saying that we should not characterize all behaviors as a Mardi Gras, but we have good areas in which there's good linking hypotheses that we can take advantage of. So let me just give you an example. One of the things that, and I apologize I could not be here yesterday, I don't know if it was talked about, but today I haven't heard any discussion about the limits that we have in terms of the cost of cortical computation of the brain. And when we try to talk about behaviors, and human behaviors in particular, I think we have to take into account that the cost of cortical computation is very high, and that given these bioenergetic constraints, we actually have to process information in selective ways. And that's one of the places, for example, that people studying neurophysiology, but also behavior, can contribute to. We know, for example, that electrophysiological recordings show that individual neurons in cortex are strongly activated when they're engaged in appropriate tasks, but they tell us very little about how many neurons may be engaged in a task. And this is important if we want to understand how cortex encodes information. For example, it comes to mind a paper that some of you may know that Peter Lenny wrote, a very elegant paper on the cost of cortical computation, in which he estimated the cost of individual spikes for the human neocortex, and then from the known energy consumption of cortex, he established that very few neurons can be active concurrently above base level. The cost of a single spike is so high that it severely limits, possibly to fewer than 1%, the number of neurons that can be substantially active concurrently. And this high cost then requires the brain not only to use sparse representational codes, but also to allocate its energy resources flexibly among cortical regions and according to the task demand. And so we need mechanisms to manage these limited resources, and chief among them may be the mechanism of selective attention. For example, there's other mechanisms like adaptation that was alluded to. And I have to say that, for example, in the case of selective attention, it's very clear that our understanding of the mechanism has advanced by the confluence of neuroimaging methods, in particular hemodynamics exploited by functional magnetic resonance imaging, which is obviously easily related to bioenergetic cost, electrophysiology, computation, and psychophysics. And I think there's no one that works at a specific level of these 4 levels that thinks that our understanding of that process could continue only at that level. And I think that's one of the most important things, that we recognize the importance of talking, but not necessarily going bottom up as it's been referred, or top down, but rather as an interactive dialogue between those levels of analysis. So for example, this morning Gary mentioned in passing normalization models. Tony later referred to them and referred to a paper by Carantini and Higer in which they talk about normalization as a canonical computation of the brain. And in response to a question about neuromodulation, Tony mentioned that there's actually a normalization model of attention by Reynolds and Higer. Our colleague David Higer and I, for example, have been testing this model at the computational, psychophysical, and neuroimaging level. And in these cases, actually, it's very easy to refer to the Mars levels of analysis. And here I disagree with you, Ned, that this is too simplistic. I actually think that one of the interesting things is that it's very clear that behavior actually plays a critical role in these 3 levels. I don't think behavior is absent from them, but rather it's because we have a good understanding of behavior, of visual attention, that it limits some of the and we have a good neurophysiological understanding, that both of them set constraints on the computational model. Both of them are informing the algorithm level. We're trying to understand how we do it, how is it that the problem selectively processes information, and also to some degree behavior is informing even at the implementation level, because we know that the kind of selective processes that we're seeing, it's taken place in particular areas, for example, in early visual areas. So I feel that the Mars levels of analysis are really important, but that rather than thinking that we need to have all the computational level well established and then go to the algorithm and finally to the implementation, or the other way around, right? That the importance of this framework is that it really allows you to have interaction. But the point that I want to stress is that behavior is actually critical for all those levels of analysis. So even in the case of orientation selectivity that Tony talked about, which is a very well studied and understood process in macaques as well as in humans and in rodents as well, at least when we talk about macaques and monkeys, we know that even that level of analysis, a simple visual process as it seems, is altered by attention, which is a cognitive mechanism. And now we have really good models that, to understand how that may be happening, but only because they're informed by these different levels of analysis. by taking into account the computation limitations, by taking into account psychophysics, by taking into account the computational work that we have. So I think that rather than thinking it has to be bottom-up or top-down, if we have learned anything about cognition and perception, actually is that these levels are interacting with each other constantly, and maybe in the approaches that we postulate, we should also be informed by that, by the fact that we have, it cannot be only bottom-up, so to speak, right? It's not that emerging things are going to happen, and then it would tell us which algorithms are important to study, and then what is that we're trying to understand, but rather there has to be an interaction among those three levels. And I know that there's concern from the scientific community that behavior, and in particular how cognition affects behavior, is not being considered as strongly as it should in this initiative. So if you agree with us, Rafa, that would be great, because then you can continue voicing that.
You should ask Cori.
Cori, if you agree with us. I mean, a lot of people I know have been communicating with different people that are participating, like Terry Sinowski and so forth, and you know, he's a strong proponent that we should take into account the interaction of these different levels, right? Not to deny anything on the more basic levels, and for example, the beautiful work and research that you propose, but there's only so much that we could explain, you know, with those 300 neurons. As it's beautiful work, but that at the same time, really, if we try to understand behavior, that we take into account that human behavior should be part of the equation. Thank you.
I'm in complete agreement with what you said overall, so I'm just going to talk about something that you made me remember that we should have talked about more, which is gating, how the brain gates between different, I'll use the word module very loosely, but different systems, I don't even want to use the word module, how the brain gates online between the different circuits that are available. So your remark about Peter Lenny and your remarks about attention, and also the conversation I had with Xiaojing Wang over coffee break, all I think pointed me to realizing when I said I really want to know how a cortical column works, the one reason to study the whole brain, or at least some larger piece of it, is there is something really interesting, especially about human cognition, about how flexible we can be. We can learn new tasks after a couple of minutes instruction, like think of a 6-year-old learning the rules to a new game. How do we do that? How do we select online which pieces of the kind of neural tools that we have available are we going to apply to particular problems? And I don't think we said much about it at this conference. I think it's a really important problem.
Just to sort of try to respond semi-intelligently without denying what you said, the example you used of a human cognitive process being selective attention is one where we actually understand quite a bit from looking at the brains of animals, right? And I would say that one of the things, at least in its initial discussions, that the Brain Initiative is viewed as an important area is understanding how what we know in human neuroscience can be related to what we know about animal brains. And for example, it's embarrassing how few animals have ever been put in an fMRI scanner to try to understand what those signals that we can measure electrophysiologically represent in terms of what the signals we can represent in terms of imaging are. So I think there hasn't perhaps been enough attention to the specific cognitive points that you raised, but I think there is a very explicit component of thinking about how animal neuroscience can be connected to human neuroscience, given the different constraints that it operates in.
Correct. So I think we agree. I mean, I chose a topic where I think we know enough that we can make these connections, and yet there's large gaps, as you're saying. But what I would like to say is that we don't have a better understanding of selective processing just by doing single unit recording or by putting people in the scanner, right? We only advance our understanding if we relate that single unit processing or those population responses to behavior, and if we have people that are, performing behavior while they're being scanned, right? And so it may be that at some level, I mean, monkey or macaque and human are easier to relate, of course, than human and rodent, and I understand that there's different strengths with different level of analysis, but my point is that if we only took the animal models, we would not understand much of the selective processing. I mean, the selective processing It's so pronounced that, as I said, it affects the most basic perceptual processes, even those that we thought that we understood really well and were immune to cognition, right? Now we know, I think there's convincing evidence that actually they're not immune to cognition, that cognition modulates the way in which we perceive even very, very early visual processes. So I think if we didn't have that information from the human, we wouldn't know that.
No, my next door neighbor, Charlie Gilbert, would argue that he's shown exactly the same thing in the V1 visual cortex of the macaque and has been showing it for a long time.
Correct, but his studies don't have very good behavior of the monkey. I know his work well. I think that it's
unrelated.
Exactly, it's not unrelated. That's the thing. I think we should emphasize more the behavior part in the animal work as well as the neural basis in the human work.
Yeah, I'm much more flummoxed on, although I agree, I believe that language is one of the most important things we possibly could study. I'm not sure how to study that at a biological level as opposed to a psychological level. But I think selective attention is an area where it is possible.
I think we do that pretty we make some progress on that. I think it's worth actually looking at what's out there. It's not so bad, and it's actually trying to really find connections to neuroscience. I would actually be more optimistic about even the language case in defense of my area.
You have up to Tom.
Just almost an orthogonal comment for the group, especially those that are not in neuroscience. I detected across the day and a half a slight misunderstanding, and certainly Rafael and Cori could clarify it if I don't have it right, but it's conflating technique and question. The principle, and why I worry about this a lot, is in the Society for Neuroscience, where I have been involved all my life and have been president. One of the deep questions asked of us as a society, early in this game, and Cori knows this very well, was what areas should be looked at? And that's like saying, what kids do you favor the best? You got 5 kids and you got 4 shirts. Who doesn't get the shirt? So you cannot make a decision as a society and say, well, we're going to look at X, but not at Y. And the reason the society had to engage this is not just because of the constituency, but because of the enormity of the question. And I think, and Rafi amplify this if I don't have it right, or certainly Cori, that what is really being applauded by the Society for Neuroscience is not the particular level of analysis, or it's the development of tools that allows anybody to ask a question. And that's a key difference. We're not saying I study learning and memory, or Cori studies behavior in worms, or Tony studies visual perception, or Risa studies cognition. It's more like, what tools do you need? What arrows do you need in your quiver we don't have now? And that informs everybody. Now, and that's why I'm less concerned about the idea that Ned raised. If you're throwing boatloads of money at stamp collecting, which I know I'm cartooning it a bit, but I think, Ned, I get your point. That worries me too. I don't think that that's the driver. I think the driver is giving us, even in the philosophy world, there must be new tools or new theories that can inform an exciting question, and you'd welcome the tool, not necessarily embracing that there's only one way to look at the question. So I just want to make the point that with the whole brain mapping issue, it's not just the idea of if we know of a connection, because I cartooned that yesterday in my comment. It's not just knowing of a connection is not going to be purely informative, as Tony would push back against, and I would too. It's more like, do we have the tools to now allow all of us to be let loose on the problem in a new way? I don't, Cori, do you buy that analysis? Okay, good.
Picking up on what Tom just said, I think that the tools that we ought to prioritize are the ones that have the best chance of bridging levels. So a tool that just gives us stamps, obviously we don't want. A tool that can tell us about the relation between stamps and some higher order principle we should spend our money on.
Okay, so maybe now is a good time to open it up to the general discussion. Let me get some of those kids up the back who are too cool for school to come down the front so you guys can be centrally part of the discussion too. But at least save me a lot of walking.
This is where the comfy chairs are.
Yeah, okay, bring the chairs with you. But yeah, anyone who wants to raise any general issues, any issues they like for the panel now, the panel can also raise questions for each other. Just go ahead.
Just to Ned's point and part of the discussion afterwards, is this a good thing to do, spend boatloads of money on mapping the brain? It seems to me Kennedy once said, we choose to go to the moon, and once it becomes part of the public consciousness that we have the capability to do this sort of mapping, very big deal. It will be done whether it's a good idea or not, or sucks money from other worthwhile projects. It seems that way.
Well, nothing is a fait accompli here. I mean, even in the European project, they have to meet benchmarks, and there are further votes, and not all the money has been allocated. Certainly not here.
Can I just respond for a second to Tom? I mean, I liked Tom's reminder that the development of tools is useful across the board, and we should embrace that. But in the presentations themselves, the presentations did argue that and I think that's what Ned was responding to, that the mere collection of data will yield the insight, right? So I think Rafael called it his emergentism hypothesis, something like that, right? So the principles will emerge, and that's a serious, big question for which and I think that we have not been given evidence for. So the tool part, I think we all embrace and are completely on board with and endorse and want funding for, of course. But that part of the talks, so there was the emergentism hypothesis, or Cori Bargmann's talk this morning. There are conceptual maps. Okay, where are they coming from? Conceptual maps are presumably scientific psychology or the cognitive sciences that should be made explicit and embraced and made part of the overall effort, not an add-on at the end.
Actually, something you're caricaturing Rafa there.
Can't hear you.
Although I'm sort of more on your side maybe than Rafa's, the global perspective of this issue, I think you were caricaturing Rafa a little bit there. So it's one thing to say that we need these tools in order to collect all this data in order to see the emergent phenomena, but it's another thing to say that those phenomena will magically emerge. I think if you read the brain activity map paper, you will see that there is some room allocated there for theory. I might like to see more than Rafa put in, but I don't think that he's saying it's magically going to emerge. You can correct me if I'm wrong. And Sean isn't here anymore, but I think I can speak for Sean in saying that he doesn't see it. Sean Hill from the European project doesn't see it that way either. I have mentioned this statistic that rankles me, which is only 8% of their budget goes to theory and ethics. They haven't carved out exactly. And so I think it should be a larger proportion, but I don't think that Sean thinks it's all going to magically emerge either.
Yeah, I think we're using the word emerge in two different senses. I meant it in the philosophical tradition sense of scale separability, that there are phenomena that can be observed at a particular level that result out of the interaction of the particles at the lower level, and that by definition are not present if you study the particle. So that's what I mean by emergent. And I gave you two examples. One of them is decision making in the leech, and another one is spatial navigation in the mouse, where you could argue that there is an emergent level description of this phenomenon that you couldn't find from single cells. And that's part of the rationale I gave for why we need new tools to be able to collect the data, to see the whole screen. But I think the idea that things will emerge, that's the second use of the verb, and that maybe you should talk about arise instead of emerge, just to make sure we're on the same page. From the data, it's a slightly different concept. I think, to me, this is it's going to be a fantastic adventure, an intellectual adventure, because we're going to be given tools to see things that no one else has seen before. And I would be very surprised if this doesn't revolutionize neuroscience, and this revolution leads to people like you in linguistics who are looking down for the primitives of the human mind, and suddenly we'll be able to fit your theories on particular pieces of data that are floating around. But yeah, it's not about collecting a lot of data and magically waiting for things to arise, but more about developing the tools to get to this next level, which I would argue is missing.
Tony has
Any of you guys want to come in on any of this?
Yeah, so look, I think part of what leads to this disagreement is the quotation you put up that said, we seem to say, data collection comes first, then comes the ideas. The crucial point is you don't know what data to collect unless you have some ideas. You have to have some hypotheses about the way the mind works in order to know what those, in order to make predictions so that you can test those hypotheses. The data comes in when you make predictions to test the hypotheses. If you just collect a lot of random data, it's what Tom called stamp collecting.
So I was actually going to make a point rather like Ned's, because I think theory is getting short shrift around here. It's not theory when you get somebody who knows some math to look at your data. Okay, and there seems to be some confusion in this room about what theory is going to mean in this context, and it means what Ned said. Okay, and I have a colleague in California who argues that the reason you can tell that biology and by extension neuroscience is immature and physics is mature is that in neuroscience, experimentalists tell theorists what to model, but in physics, modelers tell theorists tell experimentalists what to measure, right? And it's that inversion that we have to find. That's where the progress is going to be made in this map. So there's a difference between modeling and simulation on the one hand, which is the kind of stuff that I can think about doing, and what I think theory really is, a theory of how the brain actually executes important functions, which is certainly beyond my grasp, but is the kind of thing that will lead to a decision at a level beyond mine about what tools we need, what measurements we need to make, and how we're to go about testing these theories. And I share, I think, as many doubts as Ned does, that the properties that will emerge from the undoubtedly useful collection of data will lead to the generation of those theories by osmosis. I think you need theories to be developed independently.
So there's been a lot of comments of the form, bottom-up bad, working at both high and low levels good, and then you bridge the levels. And of course, everyone thinks that that's great, and the goal whereby you have mechanistic explanations of the higher level things in terms of the lower level things. But there's a worry that some of the higher levels that were being described are too many orders of magnitude away from the low level that this project is focusing on for that kind of direct bridging to really be plausible. So I was wondering if there were, the extent to which maybe the people on the panel share that worry, and if they do, what are some concrete suggestions or ways of trying to come up with some concrete proposals for finding new high levels which, though higher than the level at which this brain mapping, connectome stuff is primarily focused, are low enough that there could be some kind of direct bridging between that higher level and the level at which this research is primarily directed, so that we can, as it were, find areas where we can look where the light is best.
And I think you have some examples have even been mentioned, right? Some the work on orientation selectivity, for example, that Tony was mentioning. Regardless of whether you call the Hugel-Amdisel approach or this hierarchical approach limited, I think that approach has been very useful, and it can be modified. Actually, it has been modified by many to put sort of top-down processes into that and understand and try to have a mechanistic explanation of how it is that higher cognitive processes are affecting early levels. So I think there are several cases in which one can think, and it comes again from some studies in macaques, some in humans. When you talk about cognition in rodents, maybe we don't mean exactly the same as cognition in humans. So there's going to be a lot of gaps, but I don't think that if you take a specific problem and if you try to map it at these different levels of analysis, again, I think the Mars framework is very useful. Actually, I think that one can have that plus linking hypothesis, you can really have a better understanding of the field, and which for having whatever techniques there are to know more about the brain will be incredibly useful, right? But would not suffice by themselves if you didn't have these different levels. For example, what is that we want to understand, which would be more at the computational level.
I'd like to go back to the first comment, and I'd like to talk about computational prospection and whether that could be a stronger argument for cases such as implants for soldiers. What do I mean by that? There are certain distributions of different levels of responsibility to fear in the normal population of the soldiers. And there are techniques, computational techniques, to simulate the collective behavior of, say, 1,000, 10,000 or more nodes that have certain distributions of, say, fear. And in case we want to show that this could negatively impact the collective behavior of this network, one possibility is to simply change that distribution in a simulation. Now, of course, this depends on who does this kind of computational simulations, because you could always modulate your parameters in a way that they would give what you want. One thing that I was thinking about was, why couldn't there be a kind of contest for these kinds of projects that DARPA might, for instance, propose? A contest for computational prospection. What will happen in case we change the distribution of fear response, for instance, in a population of soldiers?
So I think that's what DARPA wants. I take it, I wish Pet was here, but I think it's early stages, but I take it that's exactly what they want to do, or some of the things that they want to start monitoring the activities, and they want to sort of do these type of projections and computations to figure out which levels, and then so that it's supposed to be, based on my understanding of it, it's supposed to be a closed loop system where they can sort of monitor these type of emotions.
I didn't mean about monitoring people, but simulating and without doing any kind of measurement on people.
Oh, I see.
Computational simulation of thousands of people that you change the distribution of fear response.
There's working game theories on that.
So I mean that there could be a way to make a case about the feasibility or the potential possibilities of these projects.
Actually, just a very, very quick comment. I know, Cori, you have your hand. David, a microphone over there. Oh.
Someone's here first.
Oh, sorry. But for example, in those simulations, and I think that's one case in which actually some social factors come into place, right? It's very well known that the more people you have responsible for something, the more dilution of responsibility, for example. So just not having any behavior that guides that computation, I don't think would be a good idea.
I just want to say, guys, this is a very interesting question, but it's not what DARPA set out to do. So this is accusing DARPA of something that it is definitely not asking. It's asking to treat people with psychiatric disorders. So you're extrapolating an extremely interesting, you guys are extrapolating an extremely interesting and important way from what DARPA is trying to do. But DARPA is in this from the perspective of the fact that more soldiers died of suicide in the last couple of years than died in enemy combat. And that they have an immense problem in the VA with people with post-traumatic stress disorder. So they are feeling the responsibility of having hundreds of thousands of people on their hands that they feel that they've damaged, that they want to do some good for. So I do think this is an incredibly interesting discussion from an ethical point of view, but I think they're kind of getting tarred with something that they never said they wanted to do.
I think you're right. Sort of the initial aim is for sort of treatment of PTSD, but just even DBS now, right? It can be used for both treatment purposes, but also for enhancement purposes. And some people, some people actually want it for enhancement purposes. And so then it raises all these issues about. So once the technology, the technology is just the technology. It has dual use. So once the technology has been developed. So there's a question about whether preemption is a kind of enhancement or a kind of treatment. So the soldier doesn't have PTSD yet. Is that an enhancement or a treatment? Some people think it's a treatment, but kind of like vaccines. Other people think vaccines are like enhancements, right? Because normally normal people get viruses, etc., etc. So it's a kind of enhancement. So there are debates about that. But the general form of the idea is that once you have that device, you can do all sorts of other things, just like the NSA, right? So you want to, initially the stated goal of the NSA is to monitor terrorists, right? But once you have the technology, you can monitor all sorts of other things besides terrorists. So I think it's something that we need to keep in mind, the dual use of technologies.
I have a lighter, more general question about that device. Is there any discussion about allowing the user who has the device in their brain to actually modify it in real time? For example, if I were in school, I might change the device to be more focused on attention, or having multiple devices in the brain that you could turn off one and on another. Is there
So right now for DBS, yes, they're because of the imperfect technology of DBS, there are patients who, when they have it turned on, they don't have the epilepsy, or they don't have the tremor from Parkinson's, but they also can't think, they can't do anything, or they can't hear very well. And so what they do is they trade off, or they have speech impediments. And so what they do is they trade off. When they want to hear, they turn it off, and so they have more tremor, but they can hear better. And so they can, but I think that's an open loop system. What DARPA wants is a closed loop system that sort of does it automatically. I'll monitor the mechanism based on the level and sort of does it by itself, kind of like automatic cars.
So I guess I was sort of imagining it to its logical extreme, that if I were at a conference, it might modulate the way that I speak in a more impressive way, or if I was at a date, it would make me more appealing in some way. So I sort of was thinking about it kind of realm.
Kind of like drinking wine.
Okay, at the back.
I'm Sheila Mark, and I'm a NYU graduate student in psychology. So thank you for having this conference here. I found it very informative. So I learned that we're mapping the brain to find cures for human illness like epilepsy. We don't know what consciousness is, but we're trying to find it by accident. And for law, we're mapping the brain in law cases right now that are not being held by our current system of law. And we're assuming a computer simulation of a mouse or rat brain has consciousness and feels pain. So my question is, what are the intentions of brain mapping? The intention of using it to find cures for human illness is a pure intention. If we use the brain to find consciousness, what are you going to do when you find it? And will brain create a more balanced world, or will it create more division?
Rafa just left. He was the one who was going to have all the answers to those questions. Anybody?
Well, one of the reasons I'm asking that is sooner or later it's going to get out to the public. You know, people not like us of the academic world. So I guess I'm questioning whether you have answers for that, for the masses, for why we have brain.
As the last man standing in the representative role here, I would say that the rationale for doing a large project in the Brain Initiative is that there couldn't be anything more fascinating than understanding the human brain, and that just in terms of discovery and knowledge, this is a fundamental human activity. It inspires us from the moment of our birth we are thinking about our own brains, we're thinking about the brains of those around us. It's a fundamental discovery. And in addition, there is an incredible amount of suffering that comes from the loss of brain functions. Every person in this room has a parent or a brother or sister, or if you're older, a child. Every one of us is connected to someone with a brain disorder, whether that's Alzheimer's or autism or schizophrenia. And that there's an immense amount of suffering out there that we cannot do anything about at the moment. And knowledge, it has in the past been a basis for alleviating suffering. So knowledge has also in the past been a source of increasing suffering and increasing problems in the world. But the solution to technology tends to be more technology, or the wise use, or these kinds of discussions about what is correct and incorrect as an approach for the future. Ultimately, it will be humans who will be using this decision, but the knowledge itself has potential for benefit and also potential to be a great accomplishment.
I would like to piggyback off of that. Outside of lab, I actually run an art science gallery focused on scientific communication at a high-profile venue in Brooklyn. And I have both the privilege and the onus of hearing public reaction to basically anything biologically related published in mainstream press, including the public reaction to this initiative. And while it is difficult for the public to understand, especially with long-term projects and even with single papers, how basic research will translate to new cures for diseases. This is true for many other projects, and I've heard the same criticism from the public for even completed projects like Human Genome Project. And I think that as scientists, we can be conscious of how we phrase things to the public, saying that we're going in 10 years to cure these diseases for you obviously is unrealistic. However, I found if I use a more accurate narrative of our goal is to make a wiring diagram from a million brain. People are very excited about that. They think that the budget that we've given is realistic. They think 10 years just to build technologies is great, especially if you start describing some of the cool technologies we could be using. I guess what I wanted to ask you, Cori, what are your thoughts on how this should be communicated to the public? Do you agree that we should kind of borrow from physics and be open that, well, we do think this will lead to public health advances? This is something that we're doing like the LHC because it's a quest for knowledge.
I think it's really important. So first of all, thank you for working in public communication because it's very important. The public has the benefits and the disadvantages of science as well as bearing the costs. And so as much as people can understand it and make knowledgeable decisions instead of just thinking, well, the experts know about it, I'll leave it to them, the better the decision-making process will be. I'm very leery of making false promises. I feel like telling people that we're going to cure them tomorrow is just not reasonable. And I think that that was one of the mistakes that happened, as people mentioned in the Genome Project early on. You know, if you look at what we were going to be able to do by now, we haven't been able to do that. And yet, a lot of knowledge has come from that. So I think there are a few things that suggest to us that knowing more about the brain will in some cases help us and in other cases not help us, but not knowing anything about it is certainly not helping us. And deep brain stimulation is an example of something that's almost crazy that it should have worked at all, but it worked, and it's the first new treatment for Parkinson's disease since levodopa, and there are 100,000 Parkinson's patients who have these things in their brain and therefore are not in wheelchairs, right? And that doesn't mean that that will be possible for everything, but the possibility that knowing more will sort of, the war on cancer people say, we didn't win, but actually there are a lot of cancers where we don't have them anymore. We don't have childhood leukemia anymore. That's basically 100% curable. And it's because it wasn't one war, it was many small battles. And I think that's the hope as well for neuroscience, is that we're a lot better at treating depression than we used to be. A few years ago, we're better at treating Parkinson's than we used to be a few years ago. That knowing more will help, even if it doesn't help everyone all at once. Maybe it's too late for your grandmother's Alzheimer's or even for my Alzheimer's, but maybe not for yours. And that over time that will come. So I think that, I think if you explain to people that things take time and that it's worth doing, it's okay. But my friend but just in terms of discovery, my friend Andrew Murray said that if you go back and figure out how much the whole space project cost, the amount of money it cost to put a man on the moon was the equivalent of a 6-pack of beer for every person in the United States. And if you put that into today's dollars, $3 billion would be a 6-pack of beer for every person in the U.S. If you ask people, would it be worth a 6-pack of beer to you to just know how the brain works? I think, a lot of people would say yes. Science is not expensive compared to a lot of other endeavors, and there's huge public support for science in general in this country. We're a pretty pro-science, pro-technology country. So I think I think both the discovery and the hope to build a foundation for something more fundamental can be defended.
I just had a question. I had a question for the panel about, I'm an advocate for social justice when it comes to diversity, and I thought if we did come up with a normal, quote-unquote, map of the brain, what that might mean for, the many people that don't fit that map, or even if you just looked at gender differences in two maps, and how maps do we need to account for biodiversity?
I mean, I guess at the most basic level, you know, what we share among all of us, I think is much more than whatever differences they may be. So I think at this stage of the game, it's much more important to understand what the similarities are. And I think it's perfectly fine to talk about the human brain, right? And every time one takes a close look at some of the so-called gender differences and so forth, you can question a lot of them. There may be some existing ones, but I think at this moment it's much more important to try to see what is common to all of us.
The other side of that is that there is a lot of emphasis from the more bottom-up people to make tools, and to make tools that can be used for people with different genders, people with different disorders, and so forth. So if you take, for example, Tony Zador's talk about sequencing the genome, if you can get that off the ground, then you could sequence lots of different people, not as opposed to doing one kinectome that might take 50 person years to do. If you could get that technique down to something that you can do for $5,000, then the possibilities multiply. That's what happened with the genome, right? Initially there was Jim Watson's genome and not a whole lot of others, but now for a reasonable amount of money you can get your own genome sequenced through your computer and so forth. So I think the hope is that these technologies will eventually scale and we'll be able to look at the diversity.
Okay, I think maybe it's getting to time to wrap up, so let's thank our panel very much.